Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll start our discussion about some applications of integrals, especially the geometrical application of the integral, which is to find the area under a curve. So let's look at a standard curve. Say this is a function y of x. So this is the y-axis, this is the x-axis, this is the origin. Let's take 2 points, x is equal to a and x is equal to b. We would like to figure out what the meaning of this expression is. Integral of a to b y dx, y of x dx rather. Right. So let's just look at any small interval at a value x. So let's say this total length is x, and let's say the thickness of this element is dx. Now dx we know is a very small quantity. That means this thickness would be very small. Now this is dx. If we assume dx is very small, we can assume that the height at these two places is almost the same, and that height would be y of x, where x is this value, right? So this is x. At this point, this length, vertical length, would be the value of y at x. Now what is y of x into dx? That is the area of this rectangle, right? Y of x into dx. Now if we move a little bit further, take another element of length dx, right, then this point would be x plus dx, right? And at that point, this height would be y of x plus dx, or y of the new value of x. And again, we can assume that these two heights are the same, so this would give me the next area. And if we add these areas, this gives us integral of a to b y dx. So integral of a to b y dx is basically this total area. That is the area between y of x, x-axis, the lines x is equal to a, and the lines y is equal to, x is equal to b. So this is the geometrical definition of the integral. Integral of y dx from a to b is basically the total area occupied between the y-axis, the x-axis, and these two lines. Now we neglected these small triangles. Let me just draw a clearer figure to show you what I mean. So let's say this is x and this is dx. Now I've drawn dx to be a little bit more enlarged, even though this should be small. So we've neglected this area, and then when we take the next value, we'll neglect this area of the triangle. And that is obviously an approximation. But we know dx is smaller than the smallest quantity imaginable. Dx is an infinitesimal change in x. And therefore, as we reduce this value of dx, make it closer and closer to 0, the area of these triangles ends up becoming smaller and smaller, such that the total area of the triangles also ends up being 0. Another way to see this would be, let's say you have a function y of x and you want to calculate the area between a and b. You could divide it into two rectangles. Calculate this area and calculate this area. And that would not give you a very accurate answer, because these two triangles area would be neglected. Instead of 2, you could actually make 4. In that case, you actually take care of more of the area and less of the area is neglected. If you take 8 rectangles or 16 or an infinite amount of rectangles, if the thickness of this element is dx, there will be an infinite amount of rectangles here. And as the number of rectangles increases, the area that we have neglected, the area in these triangles, decreases, and therefore the answer is actually close to the true value. So if we just take a simple example, this is the graph of y is equal to x squared. Let's say we want to calculate this area. This is 1 and this is 3. So we want to calculate the area between x is equal to 1, x is equal to 3, y is equal to 0, which is the x-axis, and this line y is equal to x squared. So how would we calculate that? That's quite simple. Integral from 1 to 3 y dx. That would be the answer. That would give me integral from 1 to 3 x squared dx, which we can write as x cubed by 3. Now the limits are also important. The limits are from 1 to 3, which means that we take the value of this function at 3, which will be 9, minus the value of this function at 1, which will be 1 by 3. So this gives me 9 into 3 is 27, 26 by 3. 26 by 3 units. This is the total area of this region which is under y is equal to x squared. Now this was the simple example, but we can make a number of additions to that. One small modification could be calculating the area between a curve and the y-axis. So let's say this is the function and we wanted to calculate this area. So this is y is equal to a, y is equal to b, this is the y-axis. We want to calculate this area where this is y of x. Now what we need to do is we can convert y of x to x of y, right? For example, if our y of x is equal to x square, then we can get y is equal to x square gives us x is equal to root y, which can be written as x as a function of y, right? So y of x we can write it as x of y, and now we'll do the same thing we did earlier, except we don't integrate with respect to x, we integrate with respect to y. So in this case, this area would be integral from y is equal to a to y is equal to b x dy, where x in this case is not root y because this isn't y is equal to x squared, but whatever this is from y of x, we can always get x of y, right? That gives us this sort of thing. Another thing we can do is we can ask you to find the area between two curves. In that case, you have to make one small modification. So let's say this is one curve, and let's say we have another curve like this, and we want to calculate the area between these two curves, between let's say this point that is x is equal to a and this point that is x is equal to b. Basically we want to calculate this total area, the area between these two curves from a to b, right? So let's call this y1 of x and let's call this y2 of, or it's actually better if we call it g of x and f of x. Let's call this f of x and this g of x. So now what we need to do is we'll divide it into a number of steps. First we calculate this point. What is this? This is the intersection of fx and gx. So we just put in the equation f of x is equal to g of x. This may give us a number of values of x. For example, this point, this point, this point. You just consider the value of x which lies between a and b, right? And now we'll divide the integral into these two parts. So let's call this c. So first we'll go from a to c, then we'll go from c to b. Now how do you calculate this area between a and c? If I write, I'll just label a number of points now. A, B, C, E, F, G I've already used, so H, let's say I. Right. Now what we can do is, we can calculate this total area first. What is this total area? That is the area under f of x. This curve is f of x. So that will be integral of a to c f of x. Then we can calculate this total area, which is the area under g of x. And if we subtract them, we'll get this remaining area. So minus integral of a to c g of x. Now we add in the second part. And now the difference is now gx is above f of x. So gx has a greater value between c and b than f of x. So we first take the area under the curve g of x and subtract from it the area under the curve f of x. So from c to b, g of x minus from c to b, f of x. A simpler way to write it would be integral from a to c, f of x minus g of x. Obviously there should be dx, I didn't write dx in these previous ones, plus integral from c to b, g of x minus f of x. So this is how you can calculate the area between any two curves. You just calculate the intersection points. On either side of the intersection points, one will be greater than the other generally. And so whichever one is greater, you subtract from them the smaller one. That will give you the area between these two curves. Of course, I could complicate this problem a little bit further even, and then have to calculate the area between the y-axis and these. In that case, we would have to do integral x dy instead of integral y dx.